Molecules form and rearrange in chemical reactions. Remember that fire is the result of a chemical reaction. It's actually called a combustion reaction, and fire is just one of the products. This is the chemical equation for that reaction. We have a reactant side and a product side. The heat you feel from the flames of a fire are the heat on the product side of this combustion reaction. Notice that we don't lose any matter, it just rearranges. We still have 4 oxygens, 4 hydrogens, and 1 carbon on both the product and the reactant side. This is carbonic acid. Carbonic acid is a buffer in your blood. We will talk more about buffers later, but for right now, all you need to know is that your body converts carbonic acid into CO2 and H2O. But it can also convert CO2 and H2O into carbonic acid. A great many chemical reactions are considered reversible, so instead of a single arrow, their equations have a double arrow, indicating that they can go both ways. Reversible reactions like carbonic acid will form an equilibrium. This is when the amount produced in one direction of the equation is the same as the amount produced in the other direction. Many biological processes are the result of equilibrium reactions. In a state of equilibrium, for every set of products produced, a set of products will be transferred back into reactants. Equilibrium does not mean that the reactants and products are equal in concentration, but only that their concentrations have stabilized at a particular ratio. The key point to remember is that biological processes tend to settle into an equilibrium until something changes the product or reactant quantity and thus pushes the system to a new equilibrium. Except in the most extreme physics experiments, all atoms and molecules in our universe, and especially here on Earth, are associated with some amount of energy. They jiggle, wiggle, and fly around as a consequence. This energy of motion is called kinetic energy. The more kinetic energy an atom has, the faster it is moving around. In a substance, all the atoms are moving around with their own kinetic energy. We call the average of all these movements to be the thermal energy of a substance. In other words, kinetic energy is associated with single atoms or molecules, while thermal energy is associated with compounds and substances. Thermal energy is an average of all the kinetic energy from all the atoms or molecules in the substance. As the thermal energy goes up, so does the temperature. Thermal energy and temperature are not exactly the same thing, but temperature is relatively related to thermal energy. If a substance has a low thermal energy, it will be cooler than if the same substance had a high thermal energy. If we put one substance with a lot of thermal energy together with another substance that has very little thermal energy, the atoms in those substances will start smashing into each other. The slower molecules from the low thermal energy substance will get pushed around harder and gain some energy, while the energy they gain is lost by the molecules in the high thermal energy substance. Eventually, the compound will even out in the thermal energy and temperature that is between the two starting values. An example of this from everyday life is if we took some water out of the refrigerator and poured it into a pot of boiling water. The boiling water has a lot of thermal energy, and the refrigerated water has a low thermal energy. One is hot, the other is cold. After they are mixed, the temperature of the water will be somewhere below boiling, but higher than the refrigerated water. We know that we can see this because the water molecules in the boiling water were moving fast and have slowed down, while passing that extra energy to the slow-moving molecules in the refrigerator water. Those molecules have now been sped up. When molecules transfer their energy to one another in this way, we call that transfer heat. When thermal energies of two groups of matter are changed, we say there was a transfer of heat, and we measure that with the calorie. A calorie is a unit of heat. However, the more scientific unit of heat is called a joule. Interestingly, European foods often list joules and not calories on their food packages. 1 calorie equals 4.184 joules, and 1 joule equals 0.239 calories. A calorie is defined mathematically as the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. If we rearrange this equation a little, we get the equation for the specific heat of water. Specific heat is the number of calories required to raise the temperature of 1 gram by 1 degree Celsius. The specific heat of water is 1. Other substances have different specific heats. Peanut oil has a specific heat of 0.49, and ethanol has a specific heat of about 0.58. Water has a very high specific heat relative to other fluids. What does high specific heat mean in practical terms? The higher the specific heat of some mass, the more heat energy it takes to raise the temperature of that mass. Water's high specific heat is due to its capacity to hydrogen bond. It takes more heat to break those bonds and then to speed up water molecules. It takes a harder hit to get water molecules moving. The high specific heat of water helps keep the planet from experiencing much greater and more dramatic shifts in temperature. This is why it can be cooler at night in the desert than on the beach, even though during the day the desert is much hotter. This is because there is less water in the air helping to stabilize the temperature. Previously, we looked at the masses of atoms. Each atom has a number of protons and neutrons that contribute to its mass, because each of these subatomic particles has a mass of 1 Dalton. So carbon, with 6 of each, has a mass of 12 Daltons. This is carbon's mass number. When carbon forms CO2 with 2 oxygen atoms, we can calculate the mass of CO2 by adding the mass numbers of all the atoms together. Thus, CO2 has a mass of 44 Daltons. This is 1 times 12 plus 2 times 16, which is 44. Glucose is an important sugar molecule in your body. It has a chemical formula of C6H12O6. In other words, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So what is the mass of glucose? That's right, 6 times 12 plus 12 times 1 plus 6 times 16. That equals 180 Daltons. The problem is that none of us have a scale that can measure something as small as a Dalton. And even a few grams of something would be billions of Daltons. We can convert Daltons to something more usable like grams. The conversion factor is called Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. Avogadro's number is called a mole, which is like a dozen. It is a set amount that applies to all atoms. An Avogadro number, or a mole of glucose, will weigh 180 grams. Thus, we can swap out Daltons for grams directly. So glucose has an atomic mass of 180 Daltons. We can say that it has a molar mass of 180 grams per mole. Most chemists and biologists use molar mass to talk about the weight of molecules. How would we make a 1 liter solution consisting of 1 mole of glucose dissolved in water? Well, we would measure out 180 grams of glucose and then add enough water to bring the total volume of the solution up to 1 liter. This would result in a 1 molar solution of glucose. Molarity is the number of moles of solute per liter of solution. This is the unit of concentration most often used by biologists for aqueous solutions. An acid is defined as something that donates protons to a solution. A base is something that picks up protons from a solution. Notice that the combination of the proton and the hydroxide ion makes water. In pure neutral water, the product of the concentrations of protons and hydroxide ions is always 10 to the negative 14. In mathematical terms, it looks like this. They exist in an equilibrium. If we add an acid, which adds more protons, we neutralize some of the hydroxide ions and balance out again at 10 to the negative 14th. However, there are more protons now than hydroxide ions. This solution would be considered acidic. However, if we add a base, that would add more hydroxide ions, soak up some of the protons, and leave us with less protons than hydroxide ions. This solution would be basic. It would be exceedingly difficult to talk about proton and hydroxide ion concentrations directly. I have a solution of a concentration of 10 to the negative 4 protons, said no one ever. In order to talk about whether something is acidic or basic, scientists have come up with a pH scale. In mathematical terms, pH is the negative log of the proton concentration, which looks like this. In practical terms, what this means is that as the pH goes down, it means the solution is more acidic, and as the pH goes up, that means the solution is more basic. Water is neutral and has a pH of 7. Thus we consider anything greater than 7 to be basic and anything lower than 7 to be acidic. Your blood has a pH of around 7.4, which is slightly basic. If this were to change by even more than 0.3 in any direction, you would not live long. The pH of your cells and your blood is very tightly controlled. Buffers, like carbonic acid, which we talked about earlier, are responsible for keeping your blood at the right pH. Carbonic acid is a buffer because it can be both an acid and a base, depending on the environment. Here's the equation for the reversible reaction. If too many protons show up, it pushes the equilibrium of carbonic acid back so it holds on to more protons and keeps them out of solution. If the amount of protons drop, it pushes the equilibrium of bicarbonate towards releasing protons. This back and forth equilibrium keeps your blood pH pretty stable around 7.4 and helps to keep you alive.